So if you're asked to calculate the molar solubility of a chemical in solution, well, that's not a difficult question to be able to do. We just did one previously. And so you just kind of take the KSP, find out how many ions you dissociate into to be able to solve for X. Okay, now, but what if, I know this sounds kind of strange, but what if you're taking that chemical like calcium fluoride, you say calculate the solubility, the molar solubility, same thing, of CaF2, but you're putting it into a solution that's already got another chemical in it, like NaF, and you know what the concentration of that NaF is, 0.050 in this question. Well, then how do you do that? Well, if you think about it logically, this chemical will not be able to break down as easily in that solution because of the presence already of F-negative ions in solution, so it'll be backed up. And so, therefore, the molar solubility, the solubility of it's going to decrease. But what's the calculation, and how can you calculate that decrease in solubility? Okay, since these two have an ion in common, this question is called a common ion effect question. Here's how you set it up. Well, first of all, you write the equilibrium reaction here for CaF2, because that's the chemical under consideration. We're calculating the solubility of that, so this is the chemical under consideration, don't worry about that. CaF2 is in equilibrium with the calcium ions and the fluoride ions. There. Now, what are we doing? Icebox, always. Initial, change, equilibrium. Initially, hey, we don't care about the solid sort of thing, but we know that when it breaks down, it's going to make, well, first of all, we don't have concentrations of those, but it'll break down to make X of this, and it'll make 2X of this. But wait, see that there? It isn't a zero. I gotta go back. So the deal is, what do you mean it's not a zero, chem guy? Well, it usually is, isn't it? 0, 0, and then do the change. But it's in a solution where there's already some sodium fluoride at this concentration. Which means, by the way, that when this breaks down into solution to form Na positive and F negative, it's a 1:1:1 ratio. If that's the concentration of that, that's also the concentration of the F negative ion. By the way, if there was a 2 in front here, the concentration of that would be doubled that F negative ion. Just be aware of that kind of thing. But right now, there is a concentration of this in solution initially. It's 0.050 moles per liter. Do you see that on the initial line, there actually is a chemical present? And so that's called the common ion effect. So you just go back here, you look at this over here, you say, okay, that concentration actually describes not only the Na positive, but the F negative. Great, there it is in solution. Good. Now, so that means the change is going to be, this is going to be X, and this is going to be 0.050 plus 2X. Set up your expression, KSP equals concentration of the Ca2 positive times the concentration of the F negative, but it's squared. The KSP for this, I happen to just know, is, you can look it up on a table because you're going to need it, it's 4.0 times 10 to the negative 10. And that equals, what's the concentration of the calcium? X. What's the concentration of the fluoride? It's this, 0.050 plus 2X, and that's squared. Now look at, that looks like it's a messy question, right? It looks just like you don't want to do it. Okay, watch this. Remember that if that K value is very, very small, when you divide it into the initial concentration that you have, do you have a number that is greater than or equal to 1,000? And in this case, you most certainly do. This KSP value is very, very tiny. And look, all the KSP values are so small, virtually, that you can always disregard X when they're added to or subtracted from something, even if they're multiplied by 2 to begin with, because 2 times very small is still very small. Very small minus 0.05 is still going to be 0.05. So therefore, we can get rid of all this. So really, it's 4.0 times 10 to the negative 10 equals X times 0.050 squared. And now when you do all this math, you get X equal to 1.6 times 10 to the negative 7 moles per liter when you solve for X by squaring that, dividing it into that number. Hey, what does that mean? That is X, and X actually is going to be, it is this number here that this actually loses. That is the concentration of that calcium fluoride in solution at the point where it then no longer dissolves, called the molar solubility. That's how you do it with a common ion in solution.